Just a moment. So first of all, can you see my screen?
Yes, sir.
Yeah.
Yes, Dr. Ali.
Yes. So the midterm exam on. So just keep in mind that this is because is 7310. So this was for the master's student. I mean, mainly for Amani and Venkat. And then you have other question 8310 that I'm picking. Basically, there was difference only question number one. Question number one was only for master's student. Similarly, for PhD student, he had different question for first question. So I'm coming that point. So I think question number one is fine. So Amani Venkat, did you write it properly? How does the rotor angle stability differ from the voltage stability?
I think so. I need just to grab my answer very quick because I forgot
Okay,
the
okay.
answer.
Yeah. I think you all have your hard copy. You can
Yes, I do.
match it. Uh, and then you see I have here solved those numerical problem. So what I'm going to do after the class, I will be uploading the PDF files of this question paper under the exam tab on eCourse. So then later also you can see especially the numerical problem. I mean, always you see I have solved the numerical problem. And then because I will be uploading your grades tonight, so then you can match where you made mistake, etc. And then again, if you have any question confusion, of course, and like you are welcome, you can contact me. Anyway, so therefore here you see that rotor angle stability means basically that transient stability. You have to look the rotor angle, speed, and then frequency. That is basically the rotor angle stability. So on the other hand, in case of voltage stability, you have to make sure that all voltages at each and every bus are at acceptable state. So this means here the main main dominating factor is looking the voltage. On the other hand, rotor angle means you have to look the speed or frequency and the rotor angle. That is basically the difference. So I hope both of you have written it properly. And then when controlling a synchronous generator and an induction generator, what are the main variables that should be taken care of? So for synchronous generator, as we discussed before, active power, frequency, and speed. In case of induction generator, the reactive power, voltage, and power factor. Those are the main variables. And then why is a capacitor bank connected at the terminal of an induction generator? So you all know that induction generator always draws reactive power for its magnetization. Therefore, always it has a low lagging power factor. Consequently, terminal voltage might be low. Therefore, to support the terminal voltage, to maintain rated voltage and hence rated power, a capacitor bank is always connected at the terminal of induction generator. So, Venkatamani, have you written these things?
Yes, sir. I think I
Yes, sir.
tried.
Oh, okay. Yeah. So I'll be looking after the class, and then definitely tonight you can see your guide. So therefore, you see that the PhD students, although you are not asked this question, just you look at it and you also note down it. So again, you might be asked this question maybe in the final exam. So vice versa. Okay, the question number two, you see, what is the difference between the synchronous speed of an induction generator and that of a synchronous generator? So now you see that both machine has the synchronous speed. So what is the difference? So meaning that when it is the induction generator, the synchronous speed is not actually the rotor speed or not the shaft speed. On the other hand, for synchronous generator, synchronous speed is actually the rotor speed. That is the difference. Everybody, could you follow me?
Yes.
Yes. So therefore, induction generator has two speed. One is called synchronous speed, which is the magnetization speed, magnetic field speed. But the rotary speed is different. That is related to slip. But synchronous speed for the synchronous, that is the actual rotary speed or safety speed. In other words, synchronous generator has only one type of speed, which is the synchronous speed. And that is the reason synchronous generator has the slip 0. And because induction generator has difference between synchronous speed and rotary speed, that's why there is the slip. Okay, and then this problem, so I believe everybody have done properly. So answer should be power factor 0.83. So using the inertia constant of a 2-pole 60 Hz synchronous generator 2.6, if the reactive power supplied by the generator is 410 megawatt, then calculate the system power factor provided that the moment of inertia of the machine is 26,800 kg meter square. So I hope everybody did. So just I am showing. So your answer should be 0.83. So then you match with your hard copy. Question number 3. What is the significance of DQ not transformation in power networks? So therefore it basically makes the calculation easy. It converts from time domain into non-time domain, the time independent function. That's why just by using trigonometry and algebra, you can solve the problems. So therefore DQ0 basically it converts from A phase, B phase, C phase into two axis system. One is called D axis and other one is that Q axis. And as well as it makes the calculation, it makes the operation, circuit operation easy. That is the significance. And then problem also, I hope everybody did. So here is the solution. You should be getting, I think here there was two questions. Calculate the moment of inertia. So you have to find out J, that is one thing, as well as at what power factor is the generator running. So moment of inertia, J value should be 25,875.38 kg meter square approximately. And power factor value should be approximately 0.92. Did you all get the same number?
Yes, Dr.
Okay, yeah. Therefore, I have shown here, you just look and then you match with your answer. This one, what is the disadvantage of an unbalanced power generation system? So therefore, you say if there is unbalance in the system, then there will be circulating current flow between two phases. And also because of unbalance, zero sequence current will flow through the neutral, provided that that is the Y connected system. So therefore your neutral will be overloaded and even neutral might be burnt out, might be disconnected. Or even though might not be disconnected, might just be heated, but that neutral current will start flowing through any other neutral, neighboring neutral line. So therefore connected devices to that neutral line might be affected. So those are the disadvantages. So therefore you have to tell that first there will be circulating current flow, because unbalanced means there is voltage difference like among phases. Consequently, among phases there will be circulating current that will cause heat, and also zero sequence current will flow through the neutral. So neutral might be damaged, might be cut, and even it might affect the neighboring neutral system. That is the answer. Then this on B, write down the three-phase active and reactive power equation for an unbalanced load. You see, it is not for balanced load, for unbalanced load. So the answer is not root 3 VLIL cos theta and root 3 VLIL sin theta. That is not the answer. Because unbalanced, so you have to go phase by phase. All three phases you have to treat differently, 3 times. So this means three-phase active power equation will be, for example, for phase A, VAI cosine theta A, plus for phase B, VBIB cosine theta B, plus VCIC cosine theta C. Then similarly for reactive power equation, reactive power VAIA cosine, sine theta A plus VBIB sine theta B plus VCIC sine theta C. Did you all write in that way?
Yes, Dr. Ali, I did that.
So hello, Ms. Sindhuja, are you listening?
Yes, Dr. Ali.
So did you write this thing or you wrote different thing?
Yes. Yes, I have
Okay.
written the same thing.
Okay. So and then for this problem, you see, so you see, always I draw a brief schematic. This is the generator side, and this is the load side. I think just at a glance, look the problem. A three-phase 60 Hz 6 MVA synchronous generator has balanced line-to-line voltages of 8410 volt at its terminals. If the generator is supplying power to a Y-connected balanced load of 6 MVA at a 0.8 lagging power factor, then determine the following: the total complex power absorbed by the Y-connected load, as well as what is the total impedance per phase. Two questions: total complex power as well as what is the load impedance per phase. So you see Y-connected load, and this side power source has 6 MVA 60 Hertz. This is the line-to-line voltage 8410, and this is the specification or the parameters for the load 6 MVA 0.8 for 85 lagging power factor. So you see, first what I am doing, because to calculate the complex power, you need the current, because √3 VL-IL conjugate. So you know VL, line-to-line voltage 8410, but you need to know what is the line current flowing that is going to the load. So that's why from the load information is equal to √3 VL-IL. And then I am getting IL. But because in the complex power equation, I have to consider angle because there is conjugate. So I must need to put the angle. So you see this is 0.85 cosine theta. From that you find out theta, 31.79. But then because it is lagging, so you have to put minus sign. So that's why this is your line current. And then here in complex power, because I will conjugate, so you see I have changed the sign. This is plus. And then this is volt ampere. Here I have expressed in kVA, 6 angle this one. Now you see here I just put in that polar format. You might express in rectangular format, like this P plus JQ. In that format, it is the same. Okay. And then V, I think, what was that one? Oh, load impedance per phase. So because this is load, so if you know what is the load voltage and what is the per phase current, then you are done. So we calculated this is the line current, but because this is Y, so same current is flowing through each phase. But here this is the line-to-line voltage. So you have to divide by √3 to get the phase voltage. So you see that I am doing.
Dr. Ali,
Yes.
I think the unit of complex power should be MVA.
No, I mean, original unit is volt ampere. I mean, you can express this on MVA if you like. 0.006 in that way you can express in MVA. No, not always MVA.
No, the thing is, we are given 6 megavolt ampere. That is the apparent power, right?
Yes, so then you see I changed it into 10 to the power 6. I converted into MVA here in this calculation.
Okay. So what I did is like I calculated the P and Q by using the cos phi, S cos phi and S sin phi.
Okay.
And from there, I'll get in megawatt and megawatt, right? If I just use S in mega MVA,
MVA, right? That is right.
and if I do like P plus JQ, then I'll get in, I mean, in MVA, I think. No? If I
Okay.
put both in mega
So
and mega.
therefore, can you right now check? Then did I make mistake? Then here you think that there should be another 30. Can you check this one? Oh, it looks like so. 8410. Probably then I think here it is my KVA. Then it is MVA.
Yeah, I think so. It should be MVA because the complex
Yes, Dr.
power
Ali.
magnitude should be equal to the apparent power, right?
Yeah.
So that
Oh
is
no,
given.
I think this number looks like that it should be much higher than 6,000 because
I
all
think
this,
your current is in, okay, that's an AND.
can you calculate? This is 8,410
Okay, that's
multiplied
it.
by 411. So probably probably this will be my then KVA. Yeah, it looks like by looking the number, it looks like probably I did, but I think I wrote.
Yeah, it should be in MVA, Dr. Ali. You'll
Oh,
get
so
like
this means
MVA.
this line should be KVA, right? This one here,
Yes, yes,
6,000 KVA, right? Yeah.
yes, yes.
Then here it will be. So therefore, probably when I was doing in my calculator, probably I did not notice or maybe I noticed instead of writing KVA, I wrote, and then from there I squeeze, oh, then it is KVA.
Yeah, just the typos.
Yeah. So therefore, everybody keep in mind it will be KVA here, and then accordingly MVA will be here. Yeah. Okay. Oh, and then this is the phase impedance calculation, and then you might consider the angle. I did not put the angle, just I showed the magnitude. But of course, because the current has angle, if you put angle here, then it will go in the numerator. So you can put positive angle here, 3179 with the impedance. Did you all get these results?
Yeah, I
Anyway,
got this one.
just the unit is
Dr.
different,
Ali.
but at least either in this format or if you express rectangular, it is the same thing. And of course, this is MVA as you discussed, and this is the ohm, 11, the magnitude portion. Angle will be this one, positive 31.79. Okay, so then moving forward, here there is no numerical problem. In practical power system, I think then probably two question was different from masters and PhD probably. In practical power system, small signal stability is largely a problem of insufficient damping of oscillation. What are the main causes of those oscillation? So therefore, before we discuss this one, you say there is local mode, inter-area mode, subtorsional mode, and the control mode. Local mode, inter-area mode, control mode, and subtorsional oscillation mode. Those are the region of those oscillation. Then question B, from customer's perspective, reactive power is of no use. Then why is reactive power control using appropriate devices necessary? So therefore, I believe everybody knows this answer. Because if you don't control the reactive power, then your power factor will be low lagging. There will be huge voltage drop. There will be huge power loss, especially the reactive power loss, I square X loss. Consequently, because of such losses, system efficiency will be low. And because of the low power factor, voltage drop, voltage regulation will be poor. That is the reason we have to control the reactive power, even though it is of no practical use to us. Also, what are the causes of reactive power generation in a power network? The main causes is that originally in the power plant, on the armature, you have the coils. And those coils are nothing but the inductance. So simultaneously, when active power is being generated, at the same time, some reactive power is being developed because those are basically the coil. And that coil, now you can argue then, why then we will be picking up coil because it is causing the reactive power. Because coil is needed to produce voltage. You need a magnet and you need a coil. That is the principle. So you can't avoid that. So that's why originally from the system, reactive power is being generated internally. And then power flows through the line, through transformer. You see, transformer has also inductances. primary coil, secondary coil. Along the line, there are lots of inductances. And then most of our loads, even at home, HVAC load, refrigerator, television, most of the loads are inductive in nature. Therefore, those are the sources of reactive power generation. Everybody, could you follow me?
Yes, Dr. Ali.
Yes. So I hope everybody have written or whatever you have written in your language, but at least those should be the meaning. Meaning should be the same. Okay, this one, how does a static excitation differ from a DC excitation for a synchronous generator? So you remember there are three types of excitation: static, DC, and AC excitation. So DC excitation means there is a small DC generator which is placed or mounted on the same shaft on which the magnetic field is placed. So from which the DC supply, DC excitation is provided to the magnetic field. On the other hand, static excitation means it is not a DC generator nor a AC generator. Output is directly taken from the static armature terminal, because in case of synchronous generator, armature are static, magnetic field rotate. So in case of static excitation, output voltage from the stator terminal are taken and then passed through the rectifier to convert into DC, and that converted DC voltage is supplied to the magnetic field with the help of the slip ring and brushes. So that is the difference. So this means static excitation, as the name goes, you see, you are taking the output from stator terminal, static terminal. On the other hand, DC excitation means there is a small DC generator mounted on the same shaft as the magnetic field shaft. That is the difference. Now, there is another question. A balanced three-phase delta connected load is connected to a balanced three-phase source of ABC sequence. If VAB this one and the load impedances is GAB equal to GBC, GCA this, then determine the following: the line voltages of VBC, VCA, the currents IAB, IBC, and IC of the load, and see the line currents IA, IB, and IC of the load. So therefore, as you can see, I have drawn the basic schematic. Or whatever the source is, it has the ABC sequence, and that is powering to the delta connected load. I did not even draw any coil, you see, just the symbol of delta. So therefore, GAB for any of the branch, 4.6 angle 45 degree. Now find out those line voltages. Now you see this one given, VAB, 460 angle 30 degree. Therefore, because phase sequence is ABC, that is clearly mentioned, so your VBC should be, from here you have to subtract 120. That's why I got minus 90. And then from here, again you will be subtracting another 120, that will be minus 210, and then your anti-clockwise, it is plus 150. So VC is this number. And here you are asked to find out current IAB, IBC, ICA. This means phase current and as well as the line current here, IA, IB, IC. Now first I am calculating the phase current for IAB, VAB over GAB. You see, this VAB, this is GAB. So 100 angle 15, minus 15 degree. Similarly, I calculated IBC, ICA. Then for the line current, you see, what is that line current? I mean, you can get the magnitude just by multiplying by √3. You know the relationship in case of delta. Line current is √3 times phase current. So in terms of magnitude, you will be fine, but you have to get the angle. So that's why what you have to do, everybody look, this IA current is going there, but then it is divided into two parts. This is IAB, I mean that I calculated, but then here it is not ISA, it is ICA. It is in that direction. Same thing for phase B, IBC and minus IAB. So you see, accordingly, I have written IAB minus ICA. And then if you subtract this one, this one from here, then you will, sorry, this one from here, then you will be getting angle minus 45. Similarly, IBC minus IAB, this one, and IC is this one. Did you all get the same result, same angle?
No, I missed the angle. I
Uh,
thought it will be the same for all the voltage and the current. So I got the magnitude right, but the angle, unfortunately, I missed it.
okay, got it. Yeah. No, so you have to, because that is the reason it is properly saying maintain the phase sequence ABC. Yeah,
Mhm.
yeah. That's why you have to give him the importance of the angle.
Yes.
As I said, if you just multiply by √3, then the magnitude is correct, but you
Yes.
have to get the angle. That's why you have to use this strategy, this method. That's why, as I said, after the class, I will be uploading these things under the tab exam. I will be writing, for example, solutions to the numerical problems for midterm exam one, for example. I will give, so you can find out there a PDF file. I mean, exactly this file I will upload. Okay, so the last question. In real field, some synchronous generators are equipped with low-speed turbines, while some with high-speed turbines. So except pole and frequency, is there any other factor that influences the type of the synchronous generator? Yes, so the factor is that geographical location of the world, because it is geography that will determine the type of whether it is low-speed turbine or high-speed turbine. Like if there is a lake or water is available, then you have to put the hydroelectric power project. That will be, in that case, naturally that has the low speed. So accordingly, you have to choose that salient pole machine. On the other hand, if a place coal available, gas available, and then naturally that gas turbine, that oil turbine, steam turbine, nuclear turbine, they exhibit high speed. So accordingly, you can choose non-salient pole type. So that is the meaning that except pole and frequency, what are the other factors? So other factor is that geographical location of the world. Mention the range of slip values for induction motor, induction generator, and synchronous generator. So in case of induction motor, slip varies from 0 to 1. In case of induction generator, it is negative. And for synchronous generator, slip is 0. That is only the answer. And then mention 3 methods of steady state stability enhancements. The very basic thing, that one is AVR, automatic voltage regulator, then governor, and then power system stabilizer, PSS. Those 3 are the basics methods for steady state stability. Have you all written down those answers?
Yes, Dr. Ali.
Yes?
Yes, sir.
Okay. Therefore, let me see, and then tonight you can see. And then, so is everybody fine?
Yes, Dr. Ali.
Yes,
Yes,
sir.
Dr. Ali.
Okay. So therefore, only I will discuss the question number one for the PhD, and then rest of the thing is the same. So let me stop this one, and let me open just a moment.
So Dr. Ali, I think I have different questionnaire than the one you discussed for 7C.
Oh, okay.
Yes.
Yeah. So just a moment. So this is your PhD question. I opened it. This is your question, Manoj. Can you see? 8310.
Yes, Dr. Ali. Yeah.
Like Manoj, Kamana, and then Sindhuja and Lakshmi. You see, this was your question.
Yes, Dr.
Oh,
Ali.
yeah. Yeah.
You see. So what was the last question, Manoj? Just a moment.
7C. It was about the
Oh, yeah. As I said, like I just changed something.
yeah.
For master's PhD student, there is, time to time little change, and question number one was fully different. Yeah.
I think 2 is also different.
Question number 2.
Yeah.
Oh, okay. Yeah. I think I asked them this question, how does the rotor angle stability differ from voltage, in their question number 1. Yeah.
Oh yeah.
Yeah. So in that way, I mean, there is, I think 3 is fully same.
Mm.
4 was fully same, I think. 5 was, yes, I think 5 was also the same. 6 is also the same. But 7, that part is different here. Yeah. Yes, okay. So therefore, most of the thing we discussed, only let's discuss your case, question number 1. So therefore now, Amani and Venkat, you look carefully this thing, the question number 1.
Okay.
Okay.
Yes, sir.
Because I will be asking you this question next time. You see? Yeah. So what was the question? Suppose you have a 3-phase induction motor in hand, but you need a generator. Is it possible to use that motor as a generator? Explain your answer. So what was the answer you wrote, Manoj? Hello, Manoj? Okay, Kamana, can you hear me?
Yes, Dr. Ali.
Yeah. It looks like Manoj is not responding. Is he?
No, doctor, I'm here. What is it?
Oh, so I mean, what was the answer to question number A? Suppose you have a 3-phase induction motor in hand, but you need a generator. Is it possible to use that motor as a generator? Explain your answer. So
Yes, it is possible. When you add the turbine into that, when you rotate that induction motor turbine with greater speed, then it becomes the induction generator. It will produce energy.
yes, in other words, you have to create the negative slip.
Yes.
So therefore, in order to achieve the negative slip, you have to make your rotary speed higher than the synchronous speed. Then it will start working as a generator. So that is the explanation. And then I think mention 3 methods for steady state stability environment. I think I just discussed that thing. This question is here. But I think this question was not asked to the master's student. You see, a 3-phase Y-connected induction motor is supplied by a 3-phase and 4-wire system with a line-to-line voltage of 220. And the impedance of the motor is 6.3 plus J 3.05 ohm per phase. Then determine the following: the magnitude of line current, the power factor of the motor, the 3-phase average power consumed by the motor, and the current in the neutral wire. So therefore, you see, this is the brief schematic, 3-phase 4-wire system, and it is powering to the 3-phase motor. This is 3-phase motor, Y connected. And of course, it has the neutral. So you see, I have connected the neutral to this 3-phase 4-wire system. 3-phase 4-wire means it has also the neutral. So I have connected both neutral. Now, question is, find out the magnitude of line current. What is IA, IB, or IC? So therefore, you see that line-to-line voltage is given, which is 220. So I have written VAB is VL220. And you see, impedance of the motor per phase is given. So therefore, this is GA prime N prime, for example, for this one, 6.3 plus J 3.05. So I converted into polar form. So 7 angle 25, 83. Then I am calculating the line current. I equal to V over G, but because this is Y connected system, so this voltage is line voltage, so I have to divide by √3. So that's why this is in numerator and denominator this angle. Finally, I got this one, 18.15 angle minus 25. But it is, I think, just asking find out the magnitude of the line current. So as an answer, you can say, okay, 18.15 is your magnitude of line current.
Yes, Dr.
Yes. And then it is saying the power factor of the motor. So therefore, you can go with the impedance triangle. This is the power factor angle, the G angle, 25.83. So you just make it cosine. Cosine of that angle is 0.9 approximately. And then it says three-phase average power consumed by the motor. So therefore, definitely that is active power or real power, root 3 VLIL cosine theta. So therefore, plug in those numbers. Because this is the Y-connected system, so line current, phase current is the same. That's why this magnitude, that is your IL. And then cosine theta, this number. So you should be getting 6.225 kilowatt. And then you don't need to do anything. Neutral wire current is 0 ampere because this is the balanced system.
Oh, I missed this one.
You did not answer this one?
No, I answered, but I just added like all those three in phase current and like
But no, you can sum up three current, but then the result should be 0.
yeah, there should be some vectorial summation, but yeah.
Maybe somewhere then you made mistake in the calculation.
I just put the algebraic sum, so that's the mistake I did.
Oh, okay. I mean, I did not do that. I assume that you all know. That's why I did not even show the calculation. Straightforward, I wrote 0 because it is balanced system. Okay, so everybody, Kamana, Lakshmi, Sindhuja, did you get these results properly?
Yes, Dr. Ali, I got the same.
Sorry?
Yes, Dr. Ali.
Oh, okay. Therefore, after the class, let me check and then you wait. I will notify you when it is ready. So currently, as I said, if you log in there, you cannot say. You will be noticing that it is vanished. Your exam is not there because I have logged it. So you cannot say, like once all 6 are ready, only then I will be make it available to you and then you can see. Okay, so does anybody have any specific question, comment, anything?
No, Dr. Ali.
Okay, thanks. So what I'm going to upload these things in the PDF file of these under the tab exams. You can see where I uploaded the midterm exam on. At the same place, I will be uploading. I will be writing like numerical solutions to the numerical problems for midterm exam on. That will be the file name. You can see. Then later again you can match. Okay, so then let me stop this one. And let me open today's file. Okay. Everybody see in last class you were solving, I think 8, then we were ran out of time. Today, please continue. Do you have your that note? Like you are calculating, right? Yeah.
Yes, Dr. Ali.
Yes, Dr. Ali.
Yes. Can you please find out and then start calculating?
तिम्रोमा के स्क्रिन आज
Yes, sorry. Okay. Maybe I want to talk personally something. Anyway. So please, I think Manoj, you completed, right? Number 8.
I said the answer at the end.
I think you to like 2587.92, right? Yeah.
Yes.
An angle 5.23 degree. Yeah.
Right.
Yes, that was correct. And then I think we closed the that class. Now you solve number 9.
Dr. Ali, can you repeat the answer, please?
The answer is, okay, so let me write down the answer here.
Because I got something similar, but the angle is different.
87.92. This is the, and you know that angle was how much? 5.23 degrees. 5.23 degrees. So let me highlight it. Okay. Yes. Amani, can you see? This will be the answer for this one.
Yes,
2,500.
I got 2,731.6.
You raised the voltage. Yeah.
0.6, I'm sorry. And also,
The
I
angle?
don't know where is my mistake. I always make a mistake in calculation. I don't know why. Also, the angle is not correct. I got 8.588.
So please check this one. Like Manoj got correctly. So
Yes.
yeah, yeah.
Mhm.
So everybody, Sindhuja and then Lakshmi, did you
Yes,
get?
Dr. Ali. I also got the same value last time.
Oh, okay, okay. Like so, then please, those who are done number 8, please you keep going number 9. Okay.
Dr. Ali, I did ninth problem as well. Can I cross-check my answers?
Oh, okay. Hold on, just a moment.
Okay.
Just a moment. Let me write down the answer here. 0.85 lead. So when it is 0.85 leading, so what is your result? What is the voltage value?
2286 point.
Yes, you are right. Yeah. Let me write down.
Okay.
2286.
866.3437.
Oh, okay. Just a moment. So like I just truncated. I just put 0.06. And what was the angle?
6.4382.
Oh, okay. So I got 6.45. Okay. I think you are fine. It just depends on the calculator.
Mhm.
45, yes. And hold on. So therefore this is during leading power factor. Very good. And then let me copy and paste this one. Let me write down the other answer here. Sorry. Okay. So what was the voltage when it is unity power factor?
2444.
0.58. So
244.
yeah, so
Yeah.
absolutely you are right. 2444.58.
Yes, yeah. Yeah.
Okay, and what was your angle?
6.7983.
Okay, like I got 6.8 during,
Okay.
let me write so everybody can see during unity power factor. Okay. And did you also do number 10?
No,
Lakshmi?
Dr. Ali, I was trying now.
Oh, okay, okay. Yeah, so then you keep going. So everybody say, so Manoj, when you are doing number 9, then please see that this should be the result.
Sure, Dr. Ali. Yeah.
Yeah, everybody, please see. Kamana, Sindhu, Jamani, and Venkat.
Yes, sir.
So you should be getting for number 9 this one and number 8 this result. Please, that is the reason you know that so the Amani, because always in calculator or somewhere you made mistake. That is the
Yeah, always
reason.
I do that.
Yeah, that is the reason I am making a live practice. That like always I just discussed, and that's why I am now telling you please use your calculator, pen, paper. Although we are doing remotely, we are not in person, but still you please do, and that will help you a lot.
Yes, I totally agree. And also when we share the answer for the other question, sometimes that helped me to answer on the test. For example, I remember one of the question, either one, Lakshmi or Sindhuja, she answered that question. So I still remember when she answered that question. So I like this way.
Yeah, yes. Yeah, that is the reason you see, because we are like working remotely, so still like I'm trying as much as possible to keep you engaged and still doing the very similar thing that we do during in-person
Yes,
classes.
sir. I really appreciate that. Yes, agree.
Yeah. But you see, always there is some difference because there it is face to face. So quickly I can write many things on the board. Uh, quickly I can erase. So here it is sometimes it is difficult, even though that whiteboard or PowerPoint file I can write, but that is difficult.
Yeah, but also the advantage, always there's something good and bad in
Yeah,
everything. So I
exactly.
also can go back to review the whole lecture anytime I am free. So
Yeah,
also that's good for me.
yeah. But one thing is that that I upload two things. One is that the class lecture notes, I mean these slides. I think you noticed that is just class lecture. And then after the class lecture video. I think everybody have noticed that there are two tabs on eCourse here. Under
Yes,
one
sir.
tab,
Yeah.
I just upload this material that you can see. But then there is video. But because video is moving, I mean, of course, you can see many times, you can stop and see and go back and forth. But you can get at a glance this slide also. So therefore, both things are available. So in other words, you can say three opportunities, on opportunity, just class slide, and then next opportunity, you are directly live listening to me. And then again, after the class, you are getting the video.
Yes, I'm using the video also when I study for the class, and also if I miss anything during the class, I go back to the video.
Please, everybody, please do accordingly.
Yeah.
So, Kamana, did you get
Yes,
any of,
Dr.
any of the result in 9? Number 9 has two parts. One considering leading power factor, but then the other considering unity power factor. But the parameters are from problem number 8. Venkat, are you getting any of these results?
Yeah, I got for the eighth one, sir.
Now number 8 is okay?
Yeah, yes, sir.
Okay, then now please try number 9, just the instead of
Yeah, I'm
lagging.
working on it.
Oh, okay. That will change, that everything. If you say unity, that will change your life. That's why you will get different value in each case. Please make practice. Sometimes that even though you understand problem by looking, but unless you do by pen and paper and calculator, so you cannot tell what is the exact result. So that's why you are understanding. Now you really do by pen and paper and using calculator. That is like a very good practice. As I said, again, you have the midterm exam too that will be held October 22. I mean, not that far.
Hello, Dr. Ali, are you there?
Yes. So do you have any question?
No, I'm working on number 10.
Yeah. Oh, so you are done number 9.
Yes, Dr. Ali.
So you got these results that I have written.
Yes, same result.
Oh, okay, very good. Oh, okay, then you keep going. Yeah, you try number 10.
Yeah, I too got results for 9.
Oh, you got same result.
Yes.
Okay, very good. For number 10, I think what was the question? Question is it's single phase 5 horsepower synchronous motor by if the motor produces torque of 50 Newton meter, then determines its shaft speed. Okay. Okay, so let me write down the answer. So will be first answer. Shaft speed should be 2375 RPM. Okay. Excitation field speed. Okay. So those who are attempting number 10, please see, I have written down the answer for you. Shaft speed, it should be 2374.59 RPM. Excitation field speed should be 1800 RPM. And megawatt capacity 9.12. So Amani, did you get the number 8 correctly or still you are struggling?
Oh, I did not try to answer with you, sir. I just moved to next one.
Oh, you are trying number 9? Okay.
Yeah.
Okay.
So I think I also have the same problem. So I have to check the notes when after the class. But same thing. I still
Okay.
have. There is something wrong. I don't know.
Okay.
Maybe.
So therefore, what I am doing, so Amani, I am sharing number 8 and 9. Can you see? So just a moment. Amani, can you see number 8?
Yes, sir.
Please see, and then can you check which line you made mistake? First for number 8, first one. Which line you made mistake? Please say.
Oh, okay. I think I can see my mistake right now.
So keep in mind that 4.17 was in kV, so I divide by root 3. So I converted into volt.
Yeah, I did that, but
And then current was on 31.53 ampere, angle was 31.79, so I put minus angle, and then
yeah,
so on.
I think my problem is here in the first step. So V is equal 4.17 over square root of 3.
Right,
So
right.
I got the answer. It's 2.408 kilo.
Yeah, you see that in the second line I have written that, you see.
Exactly. So when I find I,
Okay.
okay, I used for this one, I used the not 4.17. I used 2.408. This is my mistake. So why we use this one?
I don't know.
For I here to find I it's 950 over, times k over
Y-
square root of 3 times v.
Yeah.
So
So
here we use which v? V line to line or v phase?
yeah, it is line to line. In the, you see, S equal to root 3 VLL, here the line quantity.
This is my mistake. Okay.
So that's why you should be getting line current on 31.53.
So we have to use the given v, not the one we divided by square root of 3.
No. So you see,
Okay.
this equation, when I am
Mhm.
writing equation, that is the per phase equation.
Yes.
So that's why here you are dividing. But in this equation, when calculating IL,
Uh-huh.
that is S root 3 VLIL, that is the three phase apparent power. And of course, those are the line quantity. Always for every problem, when S root 3 VLIL, that is the line quantity.
Okay, I see my mistake here. My mistake is I divide by square root for 3. So I'm using the phase, the phase voltage, not the line voltage.
Mhm.
So that's why I got this number.
Okay, yeah. So that
So
would
because everything down is same process. Nothing. It's my process. I got the process correct. But my mistake here is when I find IL, I used not 4.17. I used the other 2.4, which is
okay.
that's my mistake.
Yeah.
Mhm.
So that's why I am opening for you. Therefore, you see, and then later you correct it. Yeah, you see.
Mhm. Yes, I got it now. Thank you very much.
I will be uploading this slide also. Yeah.
Okay, thank you.
I mean, that's part of today's class lecture. I will be uploading this slide also. And then for 9, you see, where you will be changing, only a little change will be. You see, can you see my question number 8
Yes.
solution, this line?
Mhm. Mhm.
In this line, everything will be same, only your angle will be different.
Mhm.
Yes,
Yeah,
so
yeah.
for 0.85 leading, you see, I am putting this on.
I made the same mistake for this one. I used the phase voltage instead of the line voltage to find the I line.
Yeah. Therefore, see,
So
and then
yeah.
accordingly for unity power factor is again at that line, it will be just this angle because with the current, you don't need to consider any angle because unity power factor. So even you don't need to start from the beginning for question
Yes.
number 9.
Yeah.
You need to start from this.
Yeah, but because I made mistake at the
Yeah,
beginning, that's
yes,
what's changed
that's
all
right.
my numbers.
So therefore, you just see and later you can attempt these things.
Yeah, right now I saw my mistake because I have to be careful next time when I'm with the line voltage or the phase voltage. I made this mistake a lot.
Yeah. Even in energy conversion class, you did that.
Yes, that's I don't know why I doing this mistake. I'm supposed to be good in these terms, the voltage line and the phase line. Thank you, Dr. Ali.
Okay. So again, I came back. So then I recommend you start number 10. Okay. So Manoj, Kamana, Sindhuja, did you all get Lakshmi the result for number 10?
Yes, Dr. Ali, I got all the values. Received.
The values that I mentioned here, everything
Yes,
same?
Dr. Ali, everything same.
Okay. Well,
Dr.
Manoj?
I got just first two number,
Oh, okay.
first two values,
Okay.
but I'm confused about the excitation field speed.
Excitation field speed, that is the synchronous speed.
Synchronous speed.
Yeah, I also got, but
That excitation
It's
field speed of the generator mean of the induction generator.
Yeah.
Sometimes it is called synchronous speed of magnetic field. Sometimes it is called excitation field speed. That is 120 F over P. Excitation field speed is 120 F over P.
yeah, okay. Yeah, I got it, Dr. Ali.
Yeah. It is not any different thing. It is the same thing. Just here the terminology is different. Sometimes simply called the synchronous speed of induction generator. Excitation, sometimes magnetic field speed. Still it is the same 120 F over P. And then calculate the third part. MWH capacity. So how about Sindhuja? Are you getting these results or?
I'm working on it, Doctor.
Okay. Venkat?
Sir, I didn't get the MVAR capacity.
Oh, okay. But did you get first two?
Yeah, first is fine.
Okay. So, okay, please check the VAR capacity.
Yeah, I'm working.
Oh, okay. Lakshmi said she already got that one as well. So Lakshmi, did you get exactly same number?
Yes, Dr. Ali, I got 9.123 MVAR.
Oh, okay. Yeah. Okay. So this is fine.
Yeah.
Okay.
Oh, Dr. Ali, I got the first one.
Oh, okay.
Yeah, I got it right.
Oh, okay. Okay.
Finally, I got something right.
Yeah. Yes. 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 After several days. Yeah. Manoj, did you get these results?
Yes, Dr. Ali. So if we have like,
All three?
yeah, if we have like B and we have XL, then we can calculate the MBR by using B square by XL, right?
Yeah, V square by XC. In this case,
I
it
mean,
is
yeah, XC, sorry. Yeah.
200. So it is right.
Yeah.
Okay. So you should be getting 9.12 megawatt.
Yeah. Initially, I was thinking like, okay, there should be, I mean, some voltage changes because there are a lot of instrument like transformer. So I was thinking like, okay, maybe I have to calculate the voltage
Oh, no.
around those things, but we don't have to do that.
Yes, yes. Okay, so therefore, you see, for everybody, I think I have that number 10 as well here. So everybody see, so Venkat, Amani, Sindhuja, everybody look number 10. I just draw this type of brief schematic for 400 MB, 11 kV on 12, and then this is synchronous motor, 5 horsepower, 15 Newton meter shaft. So speed omega of the synchronous motor, P over tau, torque. And then you see, I got this number. And then I am calculating excitation field speed. And then at last, see my calculation of reactive power across the capacitor, VC square over XC. And you know, XC means 1 over 2 pi FC. So finally, you should be getting 9.112 megawatt. So for those who are attempting number 10, then look this one and match with you where you stuck and where you are making mistake. Venkat, did you get this one?
Yes, sir. I'm working on it.
Okay, let us see my calculation. I did it. And then you match with your son and use your calculator. And get. Sindhuja, are you getting?
Yes, Dr. Ali, working on it.
Yeah, let us see. This is the solution for number 10. Oh, so then in the meantime, Lakshmi and Manoj, you can start. There are two more problems for today, only two more problems. Can you see Lakshmi and Manoj?
Yes, Dr. Ali.
Yeah. So read number 11, number 12. What you can do, can you just take a picture of it for a moment? And Manoj?
Yes, Dr. Ali, I'm taking
Can
it.
you just take a photo, this on 11, 12, and even you see the last equation.
Yes.
Including the last equation, you just read number 11. Just read, both of you read number 11.
Okay, Dr. Ali.
Yeah, just read number 11. So as you can see in the problem, this is thyristor-based capacitor. It is not thyristor-based resistor, not breaking resistor, thyristor-based capacitor. But why I am showing the last equation? Equation will be the same. You just need to replace that RBR in the equation by XC.
XC.
Yeah. Everything will be the same. So RBR will be replaced with XC, capacitive reactance. The other thing will be the same.
Okay, Dr. Ali.
Yes. Now, Manoj, with that hints, like you keep trying. So I am coming a little while so in this slide. So for everybody, again, I am going back to the previous slide. Amani, are you getting this number 10?
Yes, Dr. A, I got 9.118. It's almost 9.12.
Yes. Okay, very good. Okay.
Yeah, I got 9.15, sir.
Okay, very good. Kamana, you get the QC same?
Yes, Dr. Ali.
Okay. Then Sindhuja,
Yes, Dr. Ali, I got it.
you got it. Okay, very good. So therefore everybody done. Therefore everybody, now I am going last slide for today. There are two more problems. Then we will be done for today. Everybody read number 11. So as you can see that in this case, this is single phase induction generator and there is thyristor based capacitor connected in parallel at the terminal of the generator. Therefore, this is very similar to that thyristor based braking resistor. You see, then everybody look, we use this equation phi BR, VG square over pi RBR in parenthesis pi minus alpha plus half sine twice alpha. But because this is capacitor, so only thing that will be changed is your RBR. So instead of RBR, please put there XC, capacitive reactance. That RBR will be replaced by XC. And then definitely, instead of phi, you have to write Q.
QBR, yeah.
Yes,
QB, yes, QC.
QXC, right, QXC. Everybody, can you follow me what I said?
Yes, sir.
Yes. Amani, did you hear?
Yes, Dr. Ali, I got it.
Yeah, in this equation, I mean, instead of phi, write q, qxc, and then in the denominator, RBR will be changed to xc, and then rest of the parameter will be the same for problem number 11. Now you keep going. So now let me write down the answer for this one. You should be getting
1.667 for the, what is it, XC, and then,
so finally you have to get C, capacitor value.
yeah,
What would be the value of the capacitor? So C value. C for that, like I got two millifarad.
265.
So I got 2 millifarad, and I mean approximately 2 millifarad. And for the next problem, torque value.
Yes, Dr. 2 millifarad, I got it.
Okay, very good. And then you jump to number 12, the last problem for today. Torque.
Reactive
Yes,
power.
Dr. I also got 2 millifarads.
Okay, very good. So torque value should be 22.55 kilonewton meter. And what is that? What is the other one? The reactive power. Reactive power should be 5.27 megavar. Okay, and therefore everybody see for problem number 11, you should be getting capacitor value 2 millifarad. And for question number 12, torque value should be 22.55 kilonewton meter. And reactive power value should be 5.27 megavar. So you see that you are getting.
Yeah, I got the torque 22.55.
Uh,
546 actually, yeah.
kilonewton meter.
Yes.
Okay, and then now calculate the reactive power.
So reactive power is, yes, sine phi. Yeah, 5.268 MBR.
Yeah. So just what you see, the 5.27 megavar.
Yep.
Okay. So
Dr. Ali, I also got the same results for 12th one.
oh, okay. So both results are the same.
Yes, Dr. Ali.
Okay, very good.
Dr. Ali,
Yeah, I
for
got the answer for 12th one.
12. Yeah. Same.
Yeah, 11 I'm working on it.
Oh, okay. So, Amani, did you get 2 millifarad for 11?
Yes, sir, I got 1.995. It's
Yeah.
almost 2 millifarad. Yeah.
Very good. Okay, Kamana, did you get same thing?
Yeah, I'm still working, Dr. Ali.
Oh, okay. Sindhuja?
I'm working on it, Dr. Ali.
Okay. So you calculate and then match with these results. I think next class, Lakshmi, it's your turn to present the paper, right?
Yes, Dr. Ali, I'm working on it.
Okay. Is everybody done with number 11?
Yes, Dr. Ali.
Okay.
Yes, sir. I got the answer.
Okay. You got 2 millifarad, Venkat?
Yeah, yes, sir.
Okay. Sindhuja?
Yes, Dr. Ali.
Okay. Then everybody try number 12 and then you are done for today. So therefore for number 12, we see to calculate the torque, you know, torque is power over omega, power over speed in radian per second. So therefore from this information, find out power. You see power factor is given, MVA is given. So therefore multiplication of those two will be your power. And then what is your omega? first 120 f over p, because this is synchronous generator. So 120 f over p, and then convert into radian per second. So torque will be power over omega.
Omega.
So then you should be getting this value. And for the reactive power, it is, that cosine theta, you can convert sine theta, s sine theta, or it is the MVA, and you can get the active power. So Q equal to root over S square minus P square, or whatever. You can use the power triangle, that this is the S value, and that multiplication of this, that is P value. Easily you can get the Q value, or you go S sine theta in that way. Everybody, are you doing number 12?
Yes, sir.
Okay. Amani, and did you get same result?
I'm still working, Dr. Ali.
Okay. So I think you understood the process, right? I told torque equal to power over omega.
Yes, Dr. Ali.
Kamana, you got the both results, right, for 12?
I'm still working, Dr. Ali.
Oh, okay.
I got the same result, Dr. Ali.
Okay, very good. So now,
Yeah, I too got the results.
okay. Amani?
I'm still working. I'm sorry for late, but I got the
Okay.
process.
No,
Don't worry.
that's okay. Sindhuja, did you get any of these results for 12?
I'm also working on it, Dr.
Okay.
I got the torque right, Dr. Ali.
Okay. And then now reactive power. If you think about the power triangle, then your MVA, S is given, and then S multiplied power, that is P. So you can calculate Q or make relationship with sine theta. S multiplied by sine theta. I mean 10 MVA multiplied by sine theta is your reactive power. So from this power factor, you can, this is cosine theta, you can get sine theta, and sine theta multiplied by 10 MVA, that is your reactive power. Amani, Sindhuja, did you all get the same result for reactive power or is still calculating?
Almost there, I'm sorry. Almost there.
Okay, yeah. Kamana, you got the reactive power right?
Yes, Dr. Ali, I got both.
Okay,
I got it, Dr. Ali. It's 5.27.
okay, very good. The Sindhuja?
I'm still working on it actually. I'm in between.
Okay, so did you get the torque value same or still?
Not yet.
Okay. So you understood the process, right? The torque equal to power over angular speed omega.
Yeah.
Yeah, so therefore from this information you see 0.85 is the power factor that multiplied by 10 MVA, that will give your power P in megawatt. That
Okay.
divided by angular speed omega, that will be getting from 2 pole 60, 120 F by P, that synchronous speed equation, 120 F over P. So you will be getting 3600 RPM, then converting to radian per second by multiplying 2 pi and divide by 60. So you will be getting 377 about radian per second. So that's your torque. Torque is power over omega. So then you should be getting this value kilonewton meter. And reactive power, this 10 MVA multiplied by sine theta. Therefore, your power factor 0.85, this is your cosine theta value. From there, you calculate sine theta, corresponding sine theta. And that sine theta multiplied by 10 MVA, that is your reactive power. That's all.
Okay, Dr. Ali.
So therefore, what you do, you keep going. I'm going to upload this slide with these results as it is. And you try at your room and then you match with the results.
Okay, Dr. Ali.
Okay. Yeah.
Thank you.
Okay. So therefore, is everybody fine?
Yes,
Yes.
Dr. Ali.
Okay.
Yes, Dr. Ali.
Okay. Thank you. So then stop sharing. Of course, I'm going to upload this slide. So again, you can see. Okay.
Thank you, Dr. Ali.
Yeah, of course. Yeah.